You probably know that the computers we use each day use binary to run and talk to each other. And maybe you know that binary is all zeros and ones. The reason for this is that computers work on electricity and there are basically two signals, off or zero when there is no power and on or one when there is power. So what is binary? Binary is a number system, just like decimal numbers, the numbers that we use every day, which are represented with the digits 0 to 9. There are other number systems that are used in computing, like octal, which uses only the digits 0 to 7, and hexadecimal, which has 16 digits, and uses the letters A to F for the extra ones. But we'll look at these in future videos. Binary, by comparison, has only two digits, 0 and 1. Before we look at how to count in binary, let's recap how we count in decimals. In decimals, as we learned in school, we number our columns starting with units or ones, then tens, hundreds, thousands, and so on. Now, if we keep adding 1 in the units column, we will eventually run out of numbers to add when we reach 9. And if we add another 1, then we spill over into the tens column and start again on 0 in the units column. Similarly, if we reach 99 and add 1, we will spill over into the hundreds column and the tens and units start again at 0. Counting in binary is not too different from counting in decimals, except that where you count up to 9 in any decimal column before it overflows to the next one, you can only count to 1. So after you reach 1, it overflows into the next column, and so on. Now the number you are looking at is not 1000. Remember that each time we added only 1. Let's start counting again, this time seeing the decimal equivalent. We start at 0, then add 1, and remember that in binary it overflows to the next column after 1. 1 0 is therefore 2, 1 1 is 3. From there it overflows to 1 0 0, which is 4. Now we keep counting in the same way. The number that looks like 1000 in binary is actually 8. Now comes the next part of our puzzle. Remember how the columns in our decimal numbers were labeled units, tens, hundreds, and so on? Starting with the units or ones column, with every next column, we multiply the value of each one in that column by 10. This makes sense since there are 10 decimal digits, and every group of the next column is 10 of the previous column. Similarly, in binary, we start with 1 in the first column, and then multiply the value of each column by 2, effectively doubling it. So we start with 1 on the right, and from there on multiply each number by 2. So the next number would be 2, and then we keep multiplying each column by 2 again. 4, 8, 16, 32, and so on. Following on from what we just discovered, an effect that we should note is that in decimal, when we shift a number one place to the left, the number is multiplied by 10, and when you shift it one place to the right, you divide the number by 10. In binary, when you shift the number left one place, you're effectively multiplying it by 2 or doubling it, while shifting it to the right will cause the number to be divided by 2. With the knowledge we have gained so far, we can easily convert a binary number to its decimal equivalent. Let's look at an example. To work out the value of this binary number, we'll do the following. We'll divide our binary number up in columns, similar to how we would do with decimal numbers. Then we number the columns as we saw a moment ago. Starting on the right-hand side, the first column is 1, then 2, then we keep doubling up with each column, 4, 8, 16, 32, and so on. We can of course ignore the columns that are 0. All that is left to do is take the columns with 1s and add those together. Unlike decimals, where there could be anything from a 1 to a 9 in each column, binary can only have a 1 or a 0. This makes things simple for us. So for this example, we would add 128, 32, 8, 4, and 1, which gives us a total of 173. The binary number in this example is equal to 173 in decimal. Now that we have a good understanding of how binary numbers work, there is just some terminology that we need to clarify. In a decimal number, we refer to the individual numbers as decimal digits, or just digits, that occupy each place in the number. In binary, the digits are called binary digits, or bits for short. Another definition that we should remember is a byte. A byte is most commonly a series of 8 bits. Historically, a byte could refer to other numbers of bits, but 8 bits is so common that it is almost universally acknowledged as being a byte. Another way to refer to 8 bits is an octet, from octa, which means 8. This is less common, but it is used when people want to absolutely avoid any confusion. The values of an 8-bit byte can range from 0 to 255. This information will be useful in later videos when we deal with other topics. There is one more topic that we will touch on, and that is how negative binary numbers are represented in computers. In mathematics, you can simply put a minus sign in front of a number to indicate that it is negative. The CPUs in computers, however, only deal with series of bits, so there isn't really such a thing as a minus sign. However, people have devised a few methods to represent negative numbers in computers, and one such method is called 2's complement, which is by far the most common. It is very important to remember that these are just techniques to represent negative numbers in a computer, and that they are not part of the binary system. To repeat, in mathematics, you can just put a minus sign in front of a number to make it negative. In 2's complement, as in other methods, to represent negatives in binary numbers, the highest bit is used to indicate that a number is negative. If the highest bit is set to 0, the number is positive. If it is set to 1, it is negative. Now it's important to point out that not every binary number with a 1 in the highest bit is negative. In a computer program, a number can be signed or unsigned. If a number is signed, it is positive when the highest bit is set to 0 and negative when the highest bit is set to 1. If the number is unsigned, the highest bit is simply part of the number and it is always positive. So let's look at 2's complement specifically. With the highest bit being used to indicate the sign, the highest positive number that you can reach is 127. Once you go over that, the next number is going to be negative because remember, the highest bit is going to flip over and become a 1. So what do you think the next number is going to be? The answer may surprise you. The first negative number that you encounter is minus 128. From there, with every one you add, the number increases all the way up to minus 1, which is all ones in binary. This may seem odd and not at all intuitive, but again, we must emphasize that this is only a technique developed to represent negative numbers in computers, and it is not part of the binary system, and it is also not the only technique. The very last thing we're going to do is to see how to negate a number, or switch the sign of a number, in 2's complement. To negate a number in 2's complement requires 2 steps. We simply flip all the bits and add 1. Flipping the bits means that all zeros become 1s and 1s become zeros. Then we add 1. The result is the 2's complement negated equivalent of the number we had before. Let's try an example. Here we have a binary number that is all 1s, which in 2's complement, as we saw before, is minus 1. Now let's flip all the bits and add 1. The result is positive 1. The beauty is that this works both ways. If we start with 1, flip the bits, and add 1 again, we are back to minus 1. Well, hopefully that all made sense. If anything was unclear, let me know in the comments. Thanks for watching.